After covering the hydrogen emission spectrum, we know a few things about electrons. We know that electrons exist in discrete energy levels. We know that electrons go to the lowest energy state possible, which we call the ground state. Um, we know that those electron energy levels get closer and closer together. They converge as they get farther away from the nucleus. Now, there's some other information about electrons that most of you are probably familiar with based on past chemistry classes. And we're going to just refer to the model that you've talked about thus far as the Bohr model. So in that model, again, electrons exist in discrete energy levels. Electrons fill lower energy levels before filling higher energy levels. Most of you have learned before that the first energy level can only have 2 electrons in it, and that higher energy levels can have up to 8 electrons. Notice I have a couple of little stars next to some of these bullet points, which means we're going to come back to them and modify them a bit after today's little lecture. The outer electrons in an atom are called the valence electrons, and the outermost energy level is known as the valence shell. The number of valence electrons is going to be really important for determining how elements bond and react chemically, whether or not they're extremely reactive or very stable. And the periodic table that we use to organize the elements is largely organized based on valence electrons and electron configurations. So if you take a look at the IB periodic table, it looks like this. And you have all these different numbers. These numbers at the top are the group numbers. And these numbers along the left-hand side are the row numbers or the period numbers. So what you should know is that the group numbers give you information about the number of valence electrons. So how many electrons are in the outer shell of an atom, with just very few exceptions. Now, the group numbers have changed slightly from the old syllabus, and so the number that you care about is actually the last number. So it's organized so that every element that is in group number 1 has 1 electron in its outer shell, 1 valence electron. Every element that is in group 2 has 2 valence electrons. We're going to jump over this middle block for the time being. We will refer to it later, but for now, we're going to keep it out of our talk just to keep things simpler. If you come over here, these elements all have 3, 4, 5, 6, 7, and 8 valence electrons. The one exception being helium, which only has 2 valence electrons. The 1, 2, and 3 here, the period number refers to the number of energy levels. So hydrogen only has an electron in the first energy level. It has 1 electron because it has 1 proton. So 1 electron balances the positive charge of the proton. And so it just has 1 valence electron in that first energy level. Lithium, on the other hand, has 2 energy levels. Its first energy level is filled, and in the second energy level, it has 1 valence electron. Beryllium, 2 energy levels, and in the second energy level, it has 2 valence electrons, and so on. So you should be able to figure out from a group number and from a period number exactly where an element is located in the table, how many electron energy levels it has, and how many valence electrons it has. And so from this, we could probably recap that you guys have learned how to do sort of simplified electron arrangements, we'll call them, in the past. So for hydrogen, the electron arrangement, again, for the Bohr model, this is not the system we're going to use, but it's probably the system you've seen thus far in chemistry. For hydrogen, you could just say the electron arrangement is 1, which tells us that it has 1 electron. Helium would have an electron arrangement of 2. It has 2 protons, therefore 2 electrons. And so both these electrons are in the first energy level. For lithium, we're now in the second row of the periodic table. We know it has 3 electrons because it's atomic number 3. But now, we would put an electron arrangement of 2.1. So the dot here represents a break between the first energy level, where these 2 electrons are, and the second energy level, where this 1 electron is. Notice it's in group 1. Therefore, it should only have 1 electron in that outer shell. Keep going. So beryllium has the first 2 electrons in the first energy level, and then it has 2 electrons in the outer level. Notice it's in group 2, so it should have 2 valence electrons. And if we keep going across, it pretty much does the same thing. all the way across the table, we continually get more and more valence electrons according to the group number until we hit a maximum of 8 valence electrons at neon, 2.8. At that point, the second energy level is full, and so atoms after that will have to begin filling a third energy level. So we'll get to sodium, so we get 2.8. Those are its first 10 electrons, but now its 11th electron has to go into a third energy level. And we'll just go across this row, and I'll stop there. So we've got 2.82, and then 2.8.3, 2.8.4. You get the idea. I'm going to finish it anyway. 2.8.5, 2.8.6, 2.8.7, and finally 2.8.8. Oh man, okay, let's stretch it out. There we go. Okay, so these are the electron arrangements, the simplified electron arrangements for the first 18 elements. The dots are breaks in energy levels, so everything in period 3 has 3 occupied energy levels. Everything in row 2 has 2 occupied energy levels, and the elements in row 1 only have 1 occupied energy level. The number on the far right is the number of outer electrons. So everything in this column has 1 valence electron, 2, 3, 4, and so on. Everything on the far right has a full outer shell, a full valence shell. Normally that requires 8 electrons, but helium is so small, it only requires 2. So those are probably the way that you learn to sort of locate or talk about where all the electrons are located in an atom. And it's based on the simplified Bohr model. But as we've seen in some videos, as we've talked about in class now, or that we've just seen in videos, depending on where you're at, the electron is not so simple. And there's evidence based on sending a beam of electrons through a double slit that electrons behave as waves. They have some particle properties, but they also have some wave-like properties. And so when you apply wave equations, so equations that model the behavior of the electrons acting as waves, you actually can produce a series of three-dimensional shapes that tell you where the electron is most likely to exist. These three-dimensional shapes are thought of as the shapes are regions where electrons are most likely to exist. And these three-dimensional shapes are called orbitals. So rather than having an electron traveling around a simple circular path called an orbit, we now have these three-dimensional shapes, these three-dimensional spaces where the electrons could exist, and they're called orbitals. There's 4 different kinds of orbitals to be aware of. Each one gets a different letter for its name, and they get a different shape. And these are all based on these wave equations that are far more complicated than we're going to worry about in our course. So to a certain extent, you're just going to have to accept that these are the shapes that these equations predict. So we've got s orbitals, which take simple spherical shapes. We have p orbitals that you can think of as looking sort of like little propellers or little bow ties, or sometimes we call them dumbbell shaped. So those are p orbitals. We also have much more complicated ones, d orbitals, which have multiple lobes, 4 lobes, and even rings, and then f orbitals, which have even much more complicated shapes, multiple rings, 8 lobes, things like that. We'll barely deal at all with the f orbitals. We will deal with some atoms that have d orbitals. So there's a nice simple mathematical relationship as a result of these wave equations. So we've talked about the energy levels of electrons in an atom. In this table, we are talking about how the period tells you how many energy levels there are. So the first and simplest atoms just have 1 energy level. Any atom that's represented in the second row of the periodic table has 2 energy levels. In the third row of the periodic table, 3 energy levels, and so on. So from now on, we're going to refer to those as principal energy levels. So if you're an atom that only has 1 energy level, you'd say you have 1 principal energy level, and that is the n equals 1 principal energy level. The second energy level is the second principal energy level, the n equals 2 level. So we're going to go from there. So if you are in the n equals 1 energy level, the number of sublevels, or the number of types of orbitals, is just that number n. So in the first energy level, there is one type of orbital. Okay? In the second energy level, there are two types of orbitals. In the third energy level, there are going to be three types of orbitals. And in the fourth energy level, there are four types of orbitals. So the total number of orbitals in any given energy level is n squared. So 1 squared means that there's only one type of, only one orbital total in the first energy level. And because you can have 2 electrons in any one orbital, the number of electrons that you can have in a given energy level is 2n squared. So here's n squared, it's 1, times 2 is 2. So to summarize what that all means, in the first energy level, there's only going to be one kind of orbital. There's only going to be one orbital total, and it can hold 2 electrons. In the second energy level, there's 2 different kinds of orbitals. There are going to be 2 squared, or 4 total different orbitals, and that means that there can be 8 electrons in the second energy level. Okay, the third energy level has 3 kinds of orbitals, which means there's going to be 9 total different orbitals and a total of 18 electrons in the third energy level. So already you're seeing that that old assumption you made in simpler previous classes was that there were 8 electrons in an energy level. Well, that's all going to change now. 4 types of orbitals in the fourth energy level. 4 squared means that there's actually 16 orbitals possible in the fourth energy level, and up to 32 electrons. But to show you what that looks like in sort of a pictorial form, we've got these pictures of the orbitals. So in the first energy level, there is only one type of orbital. That's an s orbital. The s orbital is always the first kind of orbital in a given energy level. And so there's just one s orbital, and it can hold 2 electrons. So here's the 1s orbital. So for hydrogen and helium, the elements that only have one energy level, they only have one kind of orbital. Their electrons live in or exist in a 1s orbital. Okay, as we move on to the second energy level, we said that there are 2 different kinds of orbitals. There are s orbitals and there's p orbitals. Okay. Now, there's 4 total orbitals, okay, and that's because in that energy level, there's going to be a 2s orbital, and then there's going to be 3 different 2p orbitals. They're known as the 2x, or 2px, 2py, and 2pz orbitals. But in total, that makes 4 different orbitals: 2s, 2p, 2p, and 2p. Okay? And that's what this picture is trying to show you, that once this little orbital is filled, the 1s orbital, the next electrons will have to move to the second energy level. That you would have done in your electron arrangement. But now where they go, instead of just one simple giant orbit that can hold 8 electrons, they actually go to more specific locations. So the first 2 electrons in the second energy level go to the 2s orbital. And after that, the next 6 electrons will go to these 3 different 2p orbitals. And so in total, the second energy level can hold up to 8 electrons. Once the second energy level is full, you would begin to fill the third energy level, but again, starting with the s, then moving on to the p, and finally, there, as we said, there'd be 9 orbitals. Those would be the 5d orbitals that come after that, but they were too big to fit on this picture. You may have noticed that I put some boxes next to these arrows. You can imagine it would get really complicated if you had to sketch these orbital shapes whenever you had to represent where the electrons were in an atom. So we have a couple of simpler ways to represent where the electrons are in atoms. And one of them is called an orbital diagram, or a box and arrow diagram. It gives a simple or a simplified visual representation of electrons and orbitals. Electrons get represented as up and down arrows, and orbitals get represented as boxes. And if you have something like the p orbitals, where the 3 p orbitals are all equal, those 3 boxes get represented all next to each other. Okay, some principles about filling up and doing electron configurations. You don't have to know these names, but these are the general ideas. Electrons will always fill energy levels and orbitals to achieve the lowest energy, most stable configurations possible. Hund's rule says that within a sublevel, so within those p orbitals, electrons will always fill up empty orbitals before pairing up inside of a single orbital. This makes sense because electrons are all negatively charged, and therefore, in order to minimize repulsion between electrons, they're going to try to sort of get as far away from each other as possible within that lowest energy sublevel. Okay? And finally, the Pauli exclusion principle says that if electrons are in the same orbital, they must have opposite spins. And so the way that we represent electrons spinning in opposite directions is by putting arrows up and down. Okay? So I've arranged these, just the first three energy levels, showing how the energies increase. You have the 1s. This represents the first energy level. Before we would have said this is the first energy level, but now we would refer to it as the 1s orbital. The second energy level has a total of 4 different orbitals in it, which can have up to 8 electrons. The 2s fills first. Slightly higher in energy is the 2p, and the 2p can hold up to 6 electrons. After you fill the 2p, the second energy level is full, and you start to fill the 3s, followed by the 3p. Okay, and eventually we'll fill the 3d, but we'll get to that in another video. Okay, so again, you're still really just filling up energy levels, but now they are going to slightly more specific types of orbitals. Okay, the periodic table is set up to help you with this. Okay, the left-hand side we're going to refer to as the S block. The right-hand side we're going to refer to as the P block, and the middle section we'll refer to as the D block. And you'll see how that's helpful as we do a couple of practice examples. A couple of vocabulary things that I've sort of neglected. So one box represents one orbital, but I've been using the term sublevel. When you have multiple orbitals that have the exact same energy, they represent a sublevel. So the 2p is a sublevel. Within it, there are 3 distinct p orbitals. The 3p is another sublevel. And the 3d is a slightly higher energy sublevel. And it contains 5 orbitals. Okay? So people often get the terms orbitals and sublevels mixed up. So you have the third principal energy level is all of these orbitals. Okay? Within that third principal energy level is actually 3 different sublevels. You can see them here. The 3s is a sublevel, the 3p is a sublevel, and the 3d is a sublevel. And then sublevels can contain different numbers of orbitals. The s sublevel just has 1, the 3p sublevel has 3, and the 3d sublevel has 5 orbitals. Okay, so there's principal energy levels, sublevels, and then orbitals. Within orbitals, there could be up to 2 electrons. Okay? Also going to pause and backtrack a moment. What should you be able to know about the shapes of these electrons? For s electrons, you should be able to sketch their shape on a 3-dimensional axis like this, recognizing that it has a spherical shape and that the 1s is the smallest, 2 would be larger, and 3 would be larger still. You should also be able to draw p orbitals, and you should be able to draw them based on the x, y, or z letter. On an x, y, z axis, the 3-dimensional axes, the 2px runs along the x-axis, the 2py runs along the y-axis, and the 2pz runs along, or 2pz runs along the z-axis. So you should be able to draw p orbitals or s orbitals. 2p orbitals and 2s orbitals are about the same size. That's why they both have that big letter 2, or big number 2 in front of them, and the letter lets you know the shape of the orbital. Okay, We're going to try to give a few examples of these electron configurations, and then we'll try to wrap this video up because it is getting quite long. Okay, so if we're trying to do electron configurations now, so before for hydrogen we would have just said it has an electron configuration of 1. Okay, but now we're going to say it has a configuration of 1s1. Okay, so let me break down what that means. This top number right here, that's the number of electrons in that orbital. I should rephrase that, in that sublevel. Okay, and the 1s is the type of orbital. So it's the big 1 is the principal energy level, and the s is the orbital / sublevel type. And let me draw some arrows to those things. I think it'll become clearer as we do some more. So essentially what this is telling you is that hydrogen has 1 electron. Okay, there's the number of electrons, that superscript. Where is that electron? It's in the first energy level, and it's in an s orbital. Okay. Remember, we already knew that it had 1 electron, 1 valence electron. We already knew it had 1 energy level. Now we just have to learn that this block here, anytime we're dealing with elements here, we're going to refer to those electrons as s electrons. So this is our s block, and helium is a part of that block. Okay, so moving on, if we were going to do helium now, we know it has 2 electrons. You can fit up to 2 electrons in an orbital. So helium's electron configuration is now 1s2. After helium, that s orbital is full, that first energy level is full, and so we're going to move on to the second energy level. So lithium has 1s2 all filled up, and so now it begins to fill up the second energy level. The first type of orbital, again, we're in the s block over here, so we're filling up the 2, s, 1. So if you look at those period numbers and group numbers, they can still help you. Instead of just 2.1, if you look at the superscripts, actually it's 2.1. Those are still really the same, but now I have to tell you what orbitals they're in. So 1s2 fills first, and then if you look at the table 2, we're in the s block, so s and then 1. So beryllium is going to end with 2, and then we're in the s block, so s and then 2. So if I move on, I'll copy and paste for the sake of speed. Beryllium is 1s2, 2s2. The superscripts add up to the 4 electrons, and you now know where those electrons are and in what types of orbitals. When we get over here to boron, we've got 1s2, 2s2, but then as we spoke about, the 2s is full, and so at this point we have to start filling up 2 p's. So it becomes 2p1. I'm going to shrink down my font size so that we can fit it. Okay. So there's boron's configuration. Still has 3 electrons in the second energy level. The 2s and the 2p are all part of that same principal energy level, and there's the 3 electrons right there. Okay. We copy that, so this would be carbon with 4 valence electrons total. Hydrogen, 5 valence electrons. Oxygen with 6 valence electrons. Chlorine, 7 valence electrons. And finally neon with 8 valence electrons. So again, these the electrons in the highest number type of orbitals, so everything in the level 2, whether it's 2s or 2p, counts as a valence electron. So the valence electron thing hasn't changed. 1 electron, 2, 3 valence, 4 valence, 5, 6, 7, 8. Okay. Notice in electron configurations we don't have to break down the different kinds of p orbitals, the px, py, pz. We just list it as p. And so p goes from being 2p1 to 2p2, 2p3, 2p4, 2p5, 2p6. And then we're full. What we've been doing thus far are called full electron configurations. As you can imagine, this gets pretty tedious as you go down the table. So you could be asked to do a full electron configuration, but it also can be helpful to simplify, especially as we go further down. So for sodium, the next element, you would do 1s2, 2s2, 2p6, and then you'd have filled the second energy level, and so you'd start to fill up the 3, the third energy level. You'd be back in the S block, right, over here, and you're in the first column, so we know it's going to end in a 1. So notice that everything in this first column is going to end in S1, telling you that it has one electron, one outer electron in its valence shell. So that's the full electron configuration for sodium. But if we want to do what's called a noble gas configuration, it's sort of a shorthand configuration. And so instead of writing everything, this box over here, this is called a noble gas. The last group of the periodic table is called a noble gas. If we look at the periodic table, it has the symbol of neon. So this is neon's electron configuration. So instead of writing 1s2, 2s2, 2p6, I can just write neon in brackets, and that equals writing 1s2, 2s2, 2p6. And then all I have to do is write whatever comes after it. So this is a shorthand configuration for sodium. Finally, if we were going to draw an orbital diagram for sodium, we generally would just have to draw it for any electrons after neon. So we would only have to draw it for the 3s orbital. It would have one electron in it, and we would be sure to label that that is the 3s. Okay. We do one more of these, try to drive the point home. So let's pick, not the next one, let's pick another one that we haven't done yet. Let's look at phosphorus. So phosphorus is over here, element number 15. Okay, so its full configuration would be 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3. So phosphorus is right here in the periodic table, okay, which means it should have the exact same outer shell configuration as the element above it, nitrogen. So it should end in S2p3. It should have 5 valence electrons, but it's in the third energy level. So if we were going to do the entire configuration for phosphorus, make that a little bit bigger. There we go. It would be 3s2, and then it would be 3p3. Okay? And if this is a little confusing without looking at the periodic table, then obviously pause the video and take a look at the periodic table to see how it matches. Okay? Now instead of writing 1s2, 2s2, 2p6, I can replace that with neon to get the noble gas configuration. And then finally, to do an orbital diagram, I would draw boxes. So I need to draw a box for the 3s, and then I would need 3 boxes side by side. Wow, that wasn't close at all to being the same size. So we're going to erase those, we're going to copy, we're going to paste. We can do it. There we go. There we go. And there we go. So close enough. Okay. Now, if I'm going to fill up these orbitals, I've got to put, oh, we're not going to do it that way. That was a mess. So we grab our arrows. So I've got, there's my 3s2. I always fill up the 3s first, and then I start to fill up the 3p's. If you can recall, I said Hund's rule said we always put electrons in empty orbitals before doubling up. This lets the electrons be slightly farther away from each other, and that creates less repulsion, and it makes them more stable. The next electron would then have to begin doubling up, so we draw it downwards if we went on to the element sulfur. So this is the 3s and the 3p. So these are the valence electrons of phosphorus, its full electron configuration, its noble gas configuration. Again, notice that the electron configuration is sort of close to what it would have been in the old system. Okay, the old system 2, 8, 5. Here are the 2. Here's the 8, and here's the 5. Okay, we've now just gotten a whole lot more specific about where those 2, 8, and 5 are located. But we still have 5 valence electrons. We still have 3 energy levels occupied. So a lot of the things haven't changed. Okay, and as you get practice learning where the S block is, the P block is, and the D block is, these things actually become quite straightforward. So to wrap up the orbital model, instead of electrons existing in discrete energy levels, we now say that electrons exist in 3D spaces known as orbitals. Okay, this is where the electron is most likely to exist. Okay, the other parts are still mostly the same. Higher energy levels can have up to 8 electrons. Actually, higher energy levels can have up to 18 and 32 electrons. But that 8 is still going to be a special number that we're going to come back to. It still has to do with the valence electrons. So the octet rule is very important, and it's something that won't go away. Okay, I think that's plenty for now. If you go on after this slide, there are a couple pictures, but there's also the opportunity to practice doing these electron configurations. So you should try to write the full electron configuration, the noble gas configuration, and the orbital diagram for every element up through element 18 as thorough practice of this topic.